if you twalalo the shapo kulaba ama situations akwe but a machine is working okay, and then at some point yasa shimafia with no indication, and you check every single component, you check the overloads, you check any other protection system, and yonse yali moneka fiati yalifia bwino. Now usually in such cases you find that if causing more occurrences if you ma lose connection, and those yala shupa kokshita diagnose, which is or rather diagnose or troubleshoot if you want. So to allow the shapari, one way I feel you could get around situations where a system ilemitripisha on account of a loose connection from an input, and the PLC can't give you any guidance to say this is exactly what is wrong. Okay, so pakuchitefi twala chitafi insert maybe a function block twala chita insert function, and then e function we can even call it input validation. Okay, twala itafiati input validation in the sense that tulefua ile tuweba ma conditions ale causing or rather tulefua kula ishiwa ama position yama inputs, whether they are true or they are false or whatever. Okay, so the symbolic comment we can say input condition monitoring, which is to say true or false. Now again, e function, the input monitoring or the input validation. Okay, do we have okay, e function it was to create like before. It needs to be called Moody organizational block OB1, which is like the management department of this software. Okay, so again, like previously as we had shown, we need to have it called Moody OB1, and then okay, it doesn't hurt to save. So we're going to open this block, and then when this one opens, this is where the fun begins. So pakwamba, I'm just going to just create a generic circuit, which is to say, I don't know whether you can call it a generic circuit or a generic logic configuration. Generic in the sense that there's really nothing special about it. So open, maybe another open, then again output coil, and then I'm going to seal in through a normally open contact across to other normally open contacts. Okay, now what we're going to do is to assign AMA addresses to these contacts, and then of course the output coil. And for this particular instance, I'm thinking to allow AMA memory bit. So I'm going to go with memory bit 1000.0. I know, don't worry about it. This is just an illustration, okay? Or maybe I'll do this. I'll do memory bit 1.0. Okay. Again, we need to get this out of the way. And then of course, maybe I need to do this. Okay, so memory bit 1.0, then there's memory bit 1.1, and then we may need this to be memory bit 1.2, and then we need this to be memory bit 5.0, of which the same address is going to be used for is still in contact, like so. Okay, so this is basically just a typical configuration. Okay, now we're going to make some assumptions, and these assumptions are going to be that the inputs we're most interested in are protection inputs. Okay, and the other assumption that we're going to make is that our protection inputs yonse, they are going to be wired through normally closed voltage-free contacts. Okay, and then of course the other condition is that to reset this configuration by way of this position to E taken up by memory bit 1.2, we're going to assume that even the reset push button is wired through a normally closed contact, which is to say that under normal conditions, all these bits are supposed to be true. Okay, like the reset is supposed to be true, and then even the monitored signal state has to be true, because like I said, they're being wired through normally closed contacts. So that said, what would expect under normal conditions? Okay, what would expect is a situation such as the following. Okay, would expect the following situation to prevail. So we need to download this so that I show you Fiondela and Apple. Okay, unable to reach the module, yes, and I know the reason why, because Moody network configuration, Moody MPI in a Profibus, so we choose MPI, and then we try that again. Okay. Just say yes, and then we need to go run in P, and then we need to okay, maybe I can see it from there. Then let's monitor this. So what we expect to happen is the following. Because we're going to wire all the protection inputs through a normally closed contact, so within the PLC, the signal state of this is going to be true. Okay, it's going to be like true, and the reset push button again is also going to be true, right? Because we're going to wire it through a normally closed contact. Externally, the field device, that reset push button, we're going to use a normally closed contact. So even this within the PLC is going to be true. And then of course we assume that even this other contact is wired through a normally closed contact, and then of course it's going to be true. If this is changed to false, we would still latch through the ceiling contact like this. Okay, and the other way that may be of interest is that if, for instance, we had something like 100 such conditions, like if we had 1,000 or 100 output coils which needed this type of configuration, then we would need to do this like 100 times, and which is really not something that I would wish on anyone. It's tedious and it's pretty much time consuming. So we're going to insert a network, okay, and then we're going to take some nodes from this configuration, which is to say that we're going to fall back on word logic. Okay, we're going to fall back on word logic. You'd notice that in network 1, the relationship between memory bit, the normally open contact with address memory bit 1.0 and that addressed as memory bit 1.1, this basically is an AND configuration. Okay, this is basically an AND configuration. Now imagine this, right? If the monitored state, or rather the monitored input condition, was memory bit 1.0, like natukwata an input, a protection input, which, like we have said, is wired through a normally closed contact. So ngatwashita wa kuli PLC internally yala aba true. okay? But we need to monitor the condition of those inputs, okay? All those protection inputs, we need to know when they're true and when they are false, and then if for any reason they become false, we don't want the system to just self-reset. What our expectations are, it's going to be the following expectations. So because our interest will be in just monitoring this input condition, the placeholder memory bit 1.0, okay? So memory bit 1.1, we're going to use it as a comparative state, in the sense that we're going to assume that if for whatever reason we've got an input addressed to memory bit 1.0 as a protection input, we want this to always be true, okay? We want this to be always be true in the PLC, okay? But at the same time, if this was to happen, then you notice that the output coil will be true, okay? But we want this to be more like a faulted state, okay? We want this to monitor the condition as being a faulty condition, okay? So to put that into perspective, we could borrow a negation instruction like so, and then what we have is a situation like this, okay? We would have a situation like this. Our situation now will be such that, okay, let's reset this. Modify to 1, modify to 0, then modify to 1, okay? You'd notice that if the input memory assigned to memory bit 1.0 is true, and our internal check bit is also true, then the output coil memory bit addressed as 5.0 is going to be false, okay? Now this would be like the preferred state of this input, okay? So when this input, or rather when the output coil addressed as memory bit 5.0 is false, then we know that the input condition represented by memory bit 1.0 is okay, it's not in a faulted state. But if you lose the signal state addressed to memory bit 1.0 as a protection input, meaning modified to 0, then this output coil becomes true, and you know that the system is faulted, okay? If this bit is true, meaning the output coil will be false, okay? The output coil is going to be false, and then you know that the system is healthy. So that's basically the relationship that we want. So you notice that true, negation, the output coil is false. If you lose the signal state addressed to memory bit 1.0, and then of course the output coil is going to be true, meaning that the system is in a faulted state, okay? So this is how we get to do what? To monitor the state of the protection inputs. So one state we could say is this, okay? Just as an illustration, okay? Assume that memory bit 1.0 is addressed to an overload unit, okay? If you want, you can be more specific. You can say thermal overload, okay? Thermal overload unit. So we address this memory bit 1.0 as representing a thermal overload unit, and then we've wired it through a normally closed contact, okay? So wired through normally closed contact, meaning that within the PLC the signal state of memory bit 1.0 is going to be true, okay? And then we're going to think of memory bit think of memory bit 1.1 as a check bit. Okay, think of it as a check bit, and then of course memory bit 1.2 is just a reset, which is why there's normally close. So maybe we can make mention of that to say memory bit 1.2 as reset wire through normally closed contact. Okay, like so. So these are the assumptions that we're going to be working off of. Okay, we're going to assume that memory bit 1.0 is addressed to a thermal overload unit, and then it's wired through its normally closed contact. So you've got this thermal overload unit, and then Mwachita wire through a normally closed contact, so that within the PLC this is going to be true. And then itulela that memory bit 1.1 as a check bit, meaning we need this to be addressed as a true bit, or rather for this bit to have a true state. Okay, and then thereafter we want for the memory bit 1.2 to be wired through a reset push buttons normally closed contact. Okay, so this is how these are going to, this is how they're going to relate. Okay, so now, like I said, if we had 100 such inputs, protection inputs, and then we'd need to create 100 of such networks, but we'd rather not do that. So so having fallen back on word logic, we're going to think of the relationship between memory bit 1.0 and memory bit 1.1 coupled to the negation as an exclusive OR condition. So we're going to go for word exclusive OR. We're going to get this. And then of course we need to assign addresses to input 1, input 2, and of course the output side of things. Okay, which is where now we can get things like memory word 1000, and then input 2. Okay, what do we do with input 2? Okay, memory word 1002, and then the output, and then on the output side of things we're going to have memory word 2000, like so. So this relationship now is basically going to be representation of the relationship between memory bit 1.0, memory bit 1.1, and the negation. Okay, so this just does what this is doing. Okay, so we're going to have true, true, false. Okay, false, true, true. Okay, so that's how that's going to work. And then thereafter, what else do we need? What else do we need? The relationship between this parallel branch, okay? The result of memory bit 1.0, memory bit 1.1, and the negation, and memory bit 5.0 is an OR relationship, okay? So we're going to get the word OR, like so. And then we're going to get this result right here, apply it to this section as an input to the second function. And then, but you notice that the relationship now here, okay, the relationship, should we do this? Should we do this? Should we do this? No, no, no. I would rather we don't use memory word 2000 as an output, because eventually we just need one true output. So maybe in this position, let's just use memory word 1004. Okay, I think we'll be better off like that. Okay, because there's just one true output that we're interested in. So the output of the first word logic instruction, which is this output, is fed to as an input to the second word logic function. Okay, and then in this state we've covered this part. Okay, we've covered this part. So now we need to understand that eventually we need to seal in through an output bit. Okay, we need to seal in through an output bit. Okay, so I'm just going to like get an output from the word O, which I'm going to call memory word 1006. Okay, and then I'm going to get, because this result is at this point, okay, in this position, so that you know that the next relationship has to be between this position, the result at this position, the result of logic operation after this OR relationship. Okay, this parallel branch is basically maybe just an OR, and then we get the result at this position. Okay, now the relationship between this position and the reset position is an AND relationship. Okay, so word AND, we get this word AND like so, and then what we'll do is we will get this bit like right here, this word, okay, as an input to the second function, and then we need a representation, a memory word for the reset bits, okay, which we're going to call as memory word 1008, like so, and then we're going to get an output. So this output word we're going to call memory word 2000, okay, like this. And then now comes the part, because remember I said the relationship which is represented by the word O is basically this part, where we have the result of the exclusive OR relationship, as in having an OR relationship with the output coil, okay, with the output bit, which is this one here, is the output bit as a seal-in contact in that position. So this word O is going to now cater for the result of the word exclusive OR word, which is this first part of the logic, as represented by memory word 1004 as an input to the second function. Okay, and then we need to seal in through the output bit. Okay, except this time we have a whole length of bits, okay, 16 bits to be precise, to seal in through. Okay, so this basically now is the same thing. Okay, what we have here is the same thing that we have in this network 2. Okay, so let's just save this. Now, what's the other thing that we need? We spoke of the memory bit 1.1 as a check bit. Okay, so meaning we need to feed in a value into memory word 1002. So to do that, we're going to set a network, and then we're going to use a move instruction. Okay, let's go to move, get this, like so, and then we're going to move a value into memory word 1002. Okay, and then we're going to be asking, oh, but what word are we going to put in there to alert us? So, okay, advantage, what's that calculator thing? Advantage, Microsoft operating system. We get this fancy calculator like so. Scientific, what do we have? Is it the scientific I want to the programmer? I think we want the programmer. Okay, so what we want, we're talking about eMemory bit 1.1 as a check bit. We want for this to have a true state, but now since we are talking about a memory word equal bit size is 16, so we're going to choose for binary, and then we're going to just click on 16 ones or whatever true states. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so this now just goes to say that in memory word 1002 tulefwa mwingine fyama bits are true yonse because of the behavior we saw in network 1. Okay, now the hexadecimal equivalent is just ama f4. Okay, so we're going to do like w hash 16 hash 1 2 3 4 f's, like so, which takes care of the check bits. So now we've got ama bits ID 16 ID true as represented by this hexadecimal value. Okay, so we're getting this value, putting it in memory word 1002, which is this memory word 1002. Okay, and then when we do that, what's the other thing that we need to do? Reset. Okay, the other position of interest is reset. Reset. So we're going to insert another network. So to reset, what do we need to do? Again, you have to remember that because in this position we've used a normally open contact, and we've said that the reset position is actually just going to be thought of as a true state, because we're going to wire it through a normally closed auxiliary contact. Okay, so what we're going to do is this. Okay, so we're going to do normally closed. Okay, normally closed, then maybe a move instruction, and then under normal conditions, what do we want? Okay, so the external reset push button, imagine that we addressed it, or we mapped that to memory bit 1.3. Okay, if we addressed it to memory bit 1.3 as a reset, so that reset push button externally is mapped to memory bit 1.3. Okay, so there are two conditions that we want to justify. So we want, if the system is healthy, okay, if the system is healthy, and if we're claiming that externally we're going to wire the reset push button through a normally closed contact, so that we normally closed up, it means this one under normal condition will always be open. Okay, if we haven't pressed the reset push button. Tefio. Or if you want it, we can use a normally open contact just in this particular configuration. Okay, we'll do it like so, so that when the reset is healthy, okay, reset is healthy, meaning the signal state in the PLC is true, we want to move a value of ones similar to this value. Okay, we've explained how we came up with this value. So we want to move this value, and then we want to have it placed in the reset memory word. Okay, that's what we want, like so. Okay, this is the normal state of things. When the external bit, okay, when the external bit of the reset push button kudia kunse kudia because to bonfisha normally close contact, so muri PLC yalaba a true state ngaya kwata true state ayama one yonsaya yalaba moved to memory word 1008. So meaning this memory word 1008 is just going to have all bits ama ones. Okay, system healthy. But what happens in the event that you want to reset the system? Okay, you want to reset the system, then in that state EBT yalaba force, at that point we need to negate this branch. Okay, we need to negate this branch like so, and then we want to move a value of 0. Okay, we want to move 0 into the same memory word like so. So now we're able to reset, and then that's just about it. Okay, that's just about it. Then how best do we demonstrate this to see that maybe the easiest way for for you to see is we're going to do the following. Okay, insert network, and then we're going to do the same thing. Open Okay, so we're interested in which one are we interested in? We're interested in the behavior of this. Okay, so we're interested in the behavior of memory bit 1004.0. okay, as it relates to memory bit 2000.0, like so. And then what else do we need? Do we get the reset? So the reset is in this position, so we'll get normally open contact memory bit 1008.0, and then we get an output coil like so, addressed as memory bit 2000.0. okay, I think that's just about sums it up. Okay, this just about sums it up. So it'll be something like this. We may need to insert another network, or maybe we just copy the same one, then paste, then change this to bit 1. Okay, 1, then 1 again, then 1 again, then again 1, like so. Then save, download this to our PLC simulator. Then let's monitor this. And then what do we have here? And then of course we're saying that this has to be true, like so. So in that state, we notice that if at all the memory bit 1000.0 and the memory bit 1000 if at all the memory bit 1000.0 and the memory bit 1000.1 were mapped to protection inputs, right now they will be in a faulted state. Okay, again, how these are moving, I'm sure maybe you're a bit confused to say, but how are you going to be mapping these? Okay, I don't need a network, but I need a network comment, like so. The relationship is such that if we say memory bit 1000.0 will be mapped, will be in the same sequence as memory bit 1004.0, and then it will be the same bit which is going to be the resultant in memory bit 2000.0. okay, so you notice that in this particular case all the 0 bits are related. Okay, and then in the same way all the bits for bit position 1 will be related also. Okay, like bit 1, bit position 1, bit position 1, so even these will be related, like so. Okay, so that's how come I know that memory bit 1004.0 is related to memory bit 2000.0. Memory bit 1004.1 is related to memory bit 2000 0.1. Okay, and that also goes to the same thing with the reset position. Okay, for the reset, what we're just saying is that memory bit 1008.0 is related to the corresponding bit positions. Okay, so that's how come these are going to stack up. So now, how does this help us? So this is where now this simulator comes in. Okay, so if you need to see the way these bits are arranged in the memory word, it's better maybe you just choose binary as the designation. Okay, you'd notice that the memory byte 4 will be on the left side. Okay, it will be like on the left side like so, and the memory byte 5 of the memory word 1004 will be on the right like this. Okay, which is why if we're talking about let's say for instance memory, the input condition, okay, which is like memory word 1000, this memory word 1000 is going to have memory byte 1000 and memory byte 1001. Okay, so you notice that right now in memory word 1002, which is our check word as it were, we've got all the bits true. In memory byte 1002 and memory byte 1003, all these bits are true. Okay, and because of that, you notice that you may want to have an output word. Okay, memory byte 2000. Okay, so memory byte 2000 and memory byte 2001. Okay, so these would be a representation of the output word, memory word 2000 as the output word. Okay, so what it is now is that if we wanted for the signal state of this protection input in memory bit 1000.0 to be true, then we need to have this checked in. Okay, we need to have this checked in, and then of course you see that this state is now no longer false, but it's no longer true but false. And then the same thing goes for memory bit 1001. Okay, like so. So in this state, we're able to now do a system reset by way of this position. Okay, so modify to 1, or rather modify to 0, then modify to 1. So we're able to now reset the state of these outputs. Okay, so if this input condition was to be false again, you'd notice that the signal state of the output bit, memory bit 2000.0, again becomes true, which is what you don't want, because if this happens, then you know that the signal state of this protection input has now become false. Okay, so now that you're able, this allows you now to monitor the state of these inputs. Okay, it's going to allow you to monitor the state of these inputs. So again, if these become true, and then you do a system reset. So you do a system reset, and then you notice that the outputs are false, and then this being the normal state of the monitored inputs, because you notice the relationship between the inputs and the outputs. If the input is false, then the output is true. If the input is true, let's push this in. These are true, true, true. The outputs. Okay, so we need to do a system reset, modify to 1, or rather modify to 0, modify to 1. Okay, like so. And then if these become false, the output instantly gets into a faulted state. So even if these become normal, then the output still remains latched. Okay, so you need to still do a system reset, modify to 0, modify to 1. Okay, like so. And then if these become false, if these inputs become false for whatever reason, then you notice that the outputs instantly become true, just showing you that the system is in a faulty state. Okay, and then of course you can do a system reset, and then because the inputs are false, then the outputs are true. So meaning that for all the bits where the outputs are true in this configuration, that the system is faulted. Okay, but if these were to become true again, and then you did a system reset, you notice that only those bits which are false in the input word would actually have a true state in the output word. Just showing you that these bits are in a faulted state. So if it helps you to monitor your input conditions, because at this stage you can map any number of inputs, protection inputs, to this configuration, and then of course ikala chitafe yonse input ya chita transition from true to false, as in it transitions from a true state to a false state. Mwashibati ngayaka fi output nishi i input yachipangako ka transition nangula mwaisa isanga ilimu true state, mwala ishibati the cause of the trip out was because of condition. Okay, and then of course you just do a system reset, you normalize. But if again yasa trip anafuti mpang, it transitions like that, mwaisa sangati i output ko ya kilei, it means that i signal attached to memory bit 1000.0 yachipangako ka transition from true to false, nangula mwaisanga mu true state. So this is how this configuration is going to work. Okay, so this was just to show us that yonsama inputs we can actually have them monitored for the normal state, meaning ngaya chitave transition from true to false, twashibati yachiba actuated kulonde chavepa i program twashibati ubwafya bwachifumina apa. Okay, so epo twapelela pa usiku bwa lero.